Hello, 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 ladies and gentlemen, and welcome back to more of the Grade 12 Euclid paper from the year 2001, put out by the University of Waterloo. And we are at question 8. In question 8, 9, 10, these guys are all written, every single part. So we're going to have our wits about us. And question 8a. On the grid provided in the answer booklet, sketch y equals x squared minus 4, so that's a parabola right there, and y equals 2 times the absolute value of x. Now, I don't have a grid provided in the answer booklet because I don't have an answer booklet, but I do have grid paper in my notebook, so I'm just going to draw myself a grid, and I'm going to graph this. And I'm going to go over the key points of graphing these two. Okay? So, ooh, that's not a good starting axis there. So there's, oops. So not bad. Draw the arrows on your axes. And then we need to start marking off, I'll go every 2 here. Three, 4, 5, 6, 7, 8, 9, -1, -2, -3, -4, -5, -6, -7, -8, -9. Not bad. Okay. So we'll do each graph in a different color. Yes, I will pick the really darkish blue. No, that might get confusing with the graph. We'll go with the lavendery purple for the parabola. Now, my parabola was y is equal to x squared minus 4. And fortunately, this is already in vertex form. So I can see my vertex is going to be 0, -4. So -1, -2, -3, -4. It's going to pass through this point right here, and that's going to be the vertex. Okay. Now, if I want to, what I can do is I can just plot more points. And, yeah, I think I shall. So at x equals 1, we're going to be at -3. And at -1 will be -3. How about x equals 2? Well, 2 squared minus 4, that's going to be 0. Same with -2. This is going to be very symmetric about the graph, about the y-axis. How about at x equals 3? Well, 3 squared is 9, minus 4 is 5, so 1, 2, 3, 4, 5. And same with -3, we get an answer of 5. And I think we will be off the graph paper with the next one. 4 squared is 16, minus 4 is 12. Well, our graph only went up to 9, so we're sort of stuck here. So now it's time to play connect the points, but we know it's a parabola, so it's going to be kind of curvy. And I'll put little arrows at the end to show that, yes, this still keeps going. Alright, and then I guess I'll use the green for our other equation. Y equals 2 absolute value of x. There wasn't a constant term, right? No, just 2 times the absolute value of x. Okay. So we once again can just plot some points. So at x equals 0, 2 times 0, the absolute value of 0, of course, being 0, we're going to get 0 here. How about at x equals 1? Well, the absolute value of 1 is 1, so times 2. So we're going to have this point right here. And then at 2, we'll have 4. 3 will have 6, so 2, 4, 6. Okay, and we'll be off the grid at that point for the next one, so we'll just stop there. And then how about -1? Well, the absolute value of -1 is 1. And 2 times 1 is 2. So this one's also going to be very symmetric about the y-axis. And we get this V shape here. Okay, so there we've graphed both of our functions that we were given. Okay. Now I'm a little hesitant because in the, as I mentioned, this has a written symbol beside it, so I would think that maybe they want some explanation, but I really don't think there's a whole lot of explanation that you can give. You could probably give a table of values. I mean, we plotted some points. You could give the table of values there. A quick word that x squared minus 4 is in vertex form would probably not go amiss. I said it verbally, but you might want to write it down. But other than that, there's not a whole lot that can be done. I think it's written there just because they want a real answer there. Although the question says sketch, so I'm a little confused. You know what? Moving on to B part, what have we got here? We've got determine with justification all the values of k for which y equals x squared minus, so the same parabola as before, and y equals 2 absolute value of x plus k do not intersect. Okay, they do not intersect. Okay. So, what values where they don't intersect? Well, how about we draw a picture and see what that might look like? Okay, we'll do an even quicker sketch than we did before. So here we have the example of k being 0, but what about other ones? Okay. Now, the parabola is always going to be the same, so it's always going to sort of look like this. Oops. Okay. Now, we're always going to get that same V shape. It's just whether or not it's moved up or down. Now, if we move it up, we will eventually cross our parabola, because parabolas always grow faster than absolute values. Absolute values are essentially two linear functions mashed together. The two lines mashed together, and lines grow slower than parabolas, so we're going to get an intersection here. So what we need to do is not have, so this is when k is positive, and when k was 0, we still were going to get an intersection point. That's k equals 0. How about if k is negative? Well, if k is a very low negative, or a very small negative number, we're still going to get some intersections. And if we make it lower still, we might get a pair of intersections. But if we make it low enough, because parabolas grow faster, the lines will never catch up to the parabola in any sense. So we'll expect some very low values, some very negative values of k. But how are we actually going to do that? Well, it's hard to manipulate 2 absolute value of x plus k in any equation. It's because of that pesky absolute value sign. Well, the function absolute value is, as I've said, sort of 2 lines mashed together. It's negative x if x is less than 0, and it's x if x is greater than or equal to 0. Okay, so what we can do is actually break our second function to absolute value of x plus k into 2 separate functions. So we'll have negative 2x plus k if x is less than 0, and we'll have 2x plus k if x is greater than or equal to 0. Okay. So what we're going to ask is that each of these lines here not intersect our parabola on their given ranges. Okay. Now, I'm going to make a simplification here. I'm going to say, well, we only really need to check the last case. Since both graphs are symmetric, around the y-axis, it suffices to show x squared minus 4 and 2x plus k don't intersect when x is non-negative. Okay? Because if there were an intersection on the other side, on the negative side, then by symmetry there'd have to be an intersection on the positive side. So we just need to check the positive case. Now, suppose there were such an intersection. Well, how do we set up any intersection between any equations? We make them equal to one another. So x squared minus 4 must be equal to 2x plus k. Okay? And this is something that we can manipulate. We could have set up x squared minus 4 equals 2 absolute value of x plus k, but we wouldn't easily be able to manipulate it, because it's really hard. Can we add or subtract absolute value of x to both sides, that sort of thing? And how does that really help us? But now that we have no more absolute values, we can very easily manipulate this. X squared would bring the minus 2x, we bring the 2x onto the other side, and we have minus 4 minus k equals 0. So we don't want any intersections. Just double checking. Do not intersect. So we never want this to happen. So we want no values of x, no positive values of x where this happens. So since we can't easily factor this, because we don't know what k is, we're going to use the quadratic formula. Okay, and we'll get negative, so x is negative b, so that's 2, plus or minus the square root of b squared, so that's negative 2 squared, so that's 4, minus 4a, which is 1, c, which is negative 4 minus k. All over 2 times a, which is 2. Okay, so we can clean this up a little bit. I'm noticing that we've got some factors of 4. Those can come out. And the 2's will cancel out, and we're going to be left with 1 plus or minus 1 plus 4 plus k, which is just 1 plus or minus square root of 5 plus k. Okay. Now, we're looking for intersections that are negative are fine, as we noted on the last page, but we're always going to, as long as we can solve this square root here, as long as we can square root what's under the brackets, we'll definitely be able to get a positive intersection, because it'll be 1 plus a positive number will be one of our roots. So So since 1 and root 5 plus, or square root of 5 plus k are both positive, so the only way this can't work is if square root of 5 plus k must not exist. That means 5 plus k must be less than 0. And rearranging that, it means 5 must be less than, or k must be less than negative 5. Okay? If we wanted to, if we had time, what we could do is we could actually pick one, say k equals negative 6, graph that, and see for ourselves that we're not going to get an intersection. Because we'll graph it for a little bit around the y-axis, we'll see there's no intersection, and we'll be able to tell, well, the parabola is very far above our absolute value function. And so, since linear terms will not grow faster than parabolas, we'll definitely have an actual solution. I'm not going to graph one right now, but if we had time, say we have given up on 9 and 10, and we wanted to check our answers, what we could do is pick a value of k, where k is less than negative 5, and make sure that we don't have any intersections. So that's something we could do. Okay? So k less than negative 5, that should give us no intersections, and we have the math to prove it. So we're definitely good on the written solution side of everything. So on to C part. State the values of k, for which it's the same parabola, y equals x squared minus 4, and y equals 2 absolute value of x plus k, so the same function as last time, intersect in exactly 2 points. Justification isn't required. Well, we're going to try and give a little bit of justification here. I guess it might have been a difficult thing for them to work with. All right. So determine what justification was. So before we had don't intersect, now we want to intersect in exactly 2 points. So by symmetry again, we need to ensure that x squared minus 4, and we'll take the positive side again, intersect once for a positive x value. Okay? So, the reason we're asking for that is if you intersect on the right of the on the right side of the graph, by symmetry we're going to have an intersection on the left side of the graph. So we want 2 intersections overall. So one's got to be on one side, one's got to be on the other side. So we just asked that there's only 1 intersection on the positive side of the graph. Okay? So once again, what does an intersection like that look like? Well, 2x plus k, and then we had x squared minus 2x minus 4 minus k, and once again, using the exact same quadratic formula, we'll get 1 plus or minus 5 plus k. Okay? So we only want 1 non-negative root. Okay, and this is where things get tricky because, and we'll just sketch it over here. Oops. Right now I'm asking about this parabola and sort of this line. I want this intersection. This intersection I don't care about. It might occur, but it's on the negative side. And our real function actually goes up like this on the left-hand side, giving us the other intersection. So we're talking about this specific black line, but I don't care about any of its negative intersections. So I only care about how it behaves on the right side of the graph. So I'm only interested in this line intersecting the parabola in one non-negative root. Okay? Any negative roots will be fine. It doesn't matter. I don't care because they're not going to show up on the graph of 2 absolute value of x plus k. Okay? So we only want one non-negative root, so we can either have exactly one root, so we have 2 cases here. So we could have one root overall, or we could have one positive and one negative root. Okay. So it's clear that 1 plus root 5 plus k is going to be the positive root. And so we'll need 1 minus 5 plus root k, 1 minus root 5 plus k to be the negative root. Okay? So in our first situation, to have one root overall, we'll need to be doing 1 plus or minus 0. So that means root 5 plus k is equal to 0. So squaring both sides, we'll get 5 plus k is equal to 0, or k is equal to negative 5. So that's one situation. And to get our one negative root, in order to make this, ensure that this is a negative root, we need to, well, we're bringing things over to the other side. We can square both sides, so it'll still be 1 less than 5 plus k, and rearranging that, bring the 5 onto the left-hand side, we'll have negative 4 is less than k. So for k equals negative 5, I'm going to draw a picture, or k greater than negative 4, we have exactly 2 intersections. Okay, so let's just draw 2 pictures of what we've got going on here. So I think we use the purple for the parabola. So anything greater than negative 4, so how about, I don't know, negative 2 or something. We get 2 intersections here, and for the negative 5 one, what will actually happen is it will touch. It will just sort of just be tangent. Okay, so these ones are outright intersections. The lines will actually cross, but for k equals negative 5, what we'll get is it sort of they'll just brush against each other. The lines will be tangent to the parabola. All right. So we didn't need to justify that. We gave a bit of a justification. And yeah, k equals negative 5 and k greater than negative 4. Okay. So that does it for question number 8. The last question with parts, we did A, B, and C. So we'll move on to question number 9 and then finally question number 10, but we'll have to wait for those in the following video. So stay tuned, and I'll see you guys for question number 9 on the 2001 Euclid paper next time.